Here is this second derivative test example number 3. I'm taking a problem from your book and choosing what looks like maybe a more complicated one. And it's this one. So the directions are to find the relative extrema and use the second derivative test where possible. So here we go. The reason I chose this one is it's a radical function, and it looks like it's going to be a little bit more complicated than the ones we've been looking at so far. So the process is the same. You're going to find the first derivative first, find those critical numbers, and then plug them into the second derivative. So the first derivative, we're going to use the chain rule. So let me rewrite the original function. So the chain rule, derivative of the outside, leave the inside alone, and now times the derivative of the inside, which is 2x. We're going to simplify this. And the simplification is nice because the 2 times 1/2 is 1. We'll bring the x squared plus 1 to the negative 1/2 down at the bottom. So that's the first derivative. The critical numbers are where the first derivative equals 0. So in the case of a rational function, it's where the top equals 0. That would be just x equals 0. You have to worry about the bottom too. It may have an asymptote or just may be an undefined derivative, but x squared plus 1 is always positive, so that will never equal 0. So because this problem is so complex, if I was asked to find relative extrema, I would use the first derivative test. I would stop here and make my chart around x equals 0. But since the directions asked us to use the second derivative test, and we probably could use some practice with our derivatives, let's find the second derivative. So I'm going to rewrite the first derivative in unsimplified form. And then I'm going to have to use a product rule to find the second derivative. So here we go. Second derivative will be the product is the first times the derivative of the second. So that's another chain rule, very similar to the chain rule we did at the beginning of this problem. Plus the second times the derivative first. And the derivative of x is just 1. So now I'm going to clean up my derivative. If you remember, what we're going to do is clean up and then factor. So this first term cleans up pretty nicely, like this. Negative 1/2 times 2 is negative 1, and x times x is x squared. Second term also cleans up very nicely. And now we're ready to factor. We look for the common factor and use the lower of the two exponents. Since negative 3/2 is less than negative 1/2, we're going to factor out a x squared plus 1 to the negative 3/2. So here we're left with negative x squared. Here we're left with negative 1/2 plus 3/2 is 2/2, which is 1. So we're just left with x squared plus 1. Then we're going to clean up this remaining factor. Negative x squared plus x is 0, so we just have 1, which means our second derivative is 1 over x squared plus 1 to the 3/2. So now we're ready to do the second derivative test. So we have to go back to look at our critical numbers. Our critical numbers were x equals 0. So second derivative test, you just plug in that critical number into the second derivative and determine if that is positive or negative. When you plug it into our second derivative, that's going to be positive. So plug the 0 in for the x, which means we have a minimum. So we can conclude we have a minimum at x equals 0. Fill in the y coordinate. You have to look back at our original function. If I can get that down, yes. So you plug in 0 to this original function. That's the square root of 0 plus 1, which is 1. So that's it. We can conclude now that this function has a minimum at 0, comma 1. And then again, I would graph this on a graphing calculator or some kind of software, and you will see, I've already done it, you will see that it looks like this. This right here is 0, comma 1, and it checks.